So in this example here, we're asked to determine whether the function is continuous or not. So the function we're given is a piecewise function. On top it's 3 over x plus 1 if x is smaller than 0, and then the function is equal to 2x plus 1 if x is greater or equal to 0. So pause the video, try this on your own, see if you can determine whether the function is continuous or not. Okay, so the first thing that you should worry about here is the fact that the function on top is, well, the whole thing's rational. The function on top is rational. The whole thing's a piecewise function. So we're worried about a break at 0. So we want to know if the function is, if the limit exists at 0. So we're going to check for a jump discontinuity here. And the other thing I'm worried about is the fact that there's a rational function. So the other thing we have to be careful for is the fact that we may be dividing by 0. So let's go ahead and do that. So solution. So if we look at the first term over here, we have the function is equal to 3 over x plus 1. So we know that x plus 1 cannot be equal to 0, right? The denominator can't be equal to 0, so 3x plus 1, x plus 1 cannot be equal to 0. So this means that x cannot be equal to negative 1. Okay. If you stop there and you said that's the answer, you have to be very careful. First of all, the function here, 3 over x plus 1, is defined for all x values that are smaller than 0. So you have to check that. You have to ensure that this value here, that our restriction, because x cannot be equal to negative 1, does it lie in the domain? In this specific case, yes, it does, because negative 1 is definitely smaller than 0. So this is a discontinuity. So we do have a discontinuity here. Okay, so the function is not continuous. We could stop there, but since we're practicing, let's go ahead and check the limit. So we want to ensure at 0 that the left-sided limit and the right-sided limit meet. This is condition 2 for continuity. So we want to ensure that the limit as x approaches 0 from the left side of this function matches the limit as x approaches 0 from the right side of this function. From the left, we're taking the value smaller than 0, so we're going to use this function here. So we want to ensure, I should put a question mark because we don't know. If we take the limit as x approaches 0 from the left side, we have the function 3 over x plus 1. And we want to know, is that equal to the limit as x approaches 0 from the right side of this function here? So since we're going to the right, we want x values that are bigger than 0, so we're using the 2x plus 1. Substituting 0 into here, we get 3 over 0 plus 1. Is that equal to, and then on this side, we have the limit as x approaches 0 from the right. We substitute our 0 here. 2, 0 plus 1. So we get 3 over 1. Is that equal to 1? That's not true. 3 is not equal to 1. So not only do we have a discontinuity at x equals negative 1, we actually have a second discontinuity. At x equals, so discontinuity here I should rewrite at x equals negative 1. And we have a discontinuity at x equals, in this case we checked at 0. From the left side of the limit and the right side of the limit did not match. So we have to, the whole function is discontinuous. You could have stopped at the first one just to answer the question because it's asking whether it's continuous or not. So just the fact that we got the first discontinuity here, we could have stopped there. But to be more precise, we have a discontinuity at x equals negative 1, and we have another discontinuity at x equals 0. Okay. Later we're going to see how to distinguish which type of discontinuities we have. Okay. So far if you got the answer was discontinuous, the function is discontinuous, that's correct. Good. Let's do another example. This example over here is very similar to what we saw in the previous one. So again, I urge you to pause the video, try it on your own and see if you get the answer. So again, we want to know if the function is continuous or not. Let's go ahead, and the first thing I'm worried about is, again, 2 over x plus 1. We want to ensure that we have a function which is continuous here. So the x plus 1 I'm worried about because we know if we have a fraction, the denominator cannot be equal to 0. So x plus 1 cannot be equal to 0. Bringing the 1 over, we get x cannot be equal to negative 1 as we saw earlier. So in this case, do we have a discontinuity at x equals negative 1? If you're saying yes, that's wrong. Be very careful. Look at the difference. Now the function that we're using here is defined on this interval for all x values greater or equal to 1, right? So this function here, 2 over x plus 1, is discontinuous at negative 1. That's true. but we're only defining it, or we're only using him for all the x values that are bigger or equal to 1. So the fact that the discontinuity happened at -1 doesn't matter. It doesn't affect our domain. Okay, so be very careful for that. So this is fine. There's no discontinuity. Okay, so the fact that this is okay, because it's not on the domain. The next thing we have to check is the left-sided limit and the right-sided limit to ensure that at this break at 1, the left-sided limit and the right-sided limit are the same, are equal. So let's go ahead and do that. So we have to check the left-sided limit. The limit as x approaches 1 from the left side of the function, is that equal to the limit as x approaches 1 from the right side of the function. So the left-sided limit, we're using the x values that are smaller than 1, so we're using 8x minus 7. So limit as x approaches 1 from the left of 8x minus 7, and is that equal to the limit as x approaches 1 from the positive side now. So all x values bigger than 1, we're using a 2 over x plus 1. Substituting the x's with 1, we get 8 times 1 minus 7. Is that equal to 2 over 1 plus 1? 8 minus 7. Is that equal to 2 over 2? 1 equals 1. So the function is in fact continuous. If you wanted, you could have done a sketch of this as well, but when the functions become a bit difficult, you could solve it without actually sketching it. Okay, so I hope you got this, and let's keep practicing. Okay, so in this example here, we're asked to determine the interval of continuity. So find the interval for which the function here is continuous. So again, we have a piecewise function. The first function is 1 over x plus 1 if x is smaller than 0. We're going to use the function negative 2x plus 1 if x is between 0 and 2. Let's put an equal sign here. And we're going to use the function 6 over x minus 3 if essentially x is greater or equal to 2. Okay, so we have to find the intervals of continuity. So in order to do that, you're going to first find where the function is discontinuous. So my first concern is the x plus 1 over here. We have a fraction, so we know that in a fraction we can't divide by 0. So the first case, we know that x plus 1 cannot be equal to 0. Bring the 1 over, x cannot be equal to -1. Is -1 in our domain? Yes. Because we're using this function for all values of x that are smaller than 0. -1 is smaller than 0, so this is an issue. So we have a discontinuity at x equals -1. Next. So this is done. The next function that we have here is negative 2x plus 1. So y equals negative 2x plus 1 is of the form y equals ax plus b. We know that these functions here are straight lines. So straight lines are continuous, so there's no issue with the function itself on the domain from 0 to 2. What we have to ensure is that when we stop being this function here, the rational function, and began the linear function, did this occur at the same moment? Namely, what I'm saying is at 0, is the left-sided limit at 0 equal to the right-sided limit at 0 for this function here? So let's go ahead and check that. So step 2, the second thing we have to check is if the limit exists. We want to see if the limit as x approaches 0 from the left of this function is it equal to the limit as x approaches 0 from the right of this function. Okay. So from the left of 0, we're using the first function, so we're taking the limit as x approaches 0 from the left of 1 over x plus 1, and is that equal to the limit as x approaches 0 from the right, which means we're using this function here, negative 2x plus 1. Because remember, this function here, the linear function, is on the interval for x values that are greater or equal to 0. So if we're taking the limit as x approaches 0 from the right side, that's greater or equal to 0, so we have to use this function here. So now we substitute our limit, we replace our x's with 0, we get 1 over 0 plus 1. Is that equal to, and we replace the limit here, negative 2 times 0 plus 1. This gives us 1. Is that equal to 1? Yes. So there's no discontinuity at this value here. So the left-sided limit, this one here, when it ends, this one begins at the same moment. So we're good. There's no discontinuity. Next, the next issue that I see here is the third function. Let's say the third piece. We have 6 over x minus 3. So let me erase this. The third thing I'm going to check is the denominator over here. We have our fraction, we know the denominator can't be equal to 0, so we know x minus 3 cannot be 0. Which means that x cannot be equal to 3. Is 3 on our domain? Well, the x values that we're using here is for all x values greater or equal to 2. 3 is in that interval, because 3 is greater than 2. That means we do have a discontinuity. At x equals 3. Okay. So we have two discontinuities here. And then the last thing we have to check is at the break of 2. So we have this break. We check the break at 0 if the functions were continuous. In this case here, yes. But we have to check at 2. When we stopped being the linear function and we started being the rational function, did this occur at the same moment? Okay, so let's go ahead and check that. So the fourth thing we have to check is the left limit as x approaches. Now we're doing 2 from the left side of the function. Is that equal to the limit as x approaches 2 from the right side of this function? So the limit as x approaches 2 from the left side, we're using this function here, the linear function, negative 2x plus 1. Is that equal to the limit as x approaches 2 from the right side of this function here, 6 over x plus 3, x minus 3. Substitute the 2, giving us negative 2 times 2, I should be putting a question mark, plus 1. Is that equal to question mark 6 over 2 minus 3? Here we get negative 4 plus 1, negative 3. Is that equal to 6? Here we get negative 6. So it's not equal to. So that means we have a discontinuity at 2 as well. Because we checked the left-sided limit and the right-sided limit at 2 and they did not meet. So at x equals 2. So if it's discontinuous at negative 1, 3, and 2, where is it continuous? Here we're dealing with linear functions which are continuous. This is a polynomial. We saw in a previous theorem that polynomials are continuous. Rational functions are continuous on their domain. So everywhere else except at negative 1 and at 3, the function is continuous. So the interval of continuity of this entire function here, the interval of continuity, I will see. I'm going to abbreviate it, I will see, interval of continuity. Is one way of writing this is all real numbers. This is, I think, the easier notation. All real numbers. So this is negative infinity to positive infinity. And then we put a bar, except, open bracket, and then we put our numbers. All real numbers except negative 1, 2, and 3. Okay, so that's the interval of continuity. If you don't like this notation, you could also write this as this is or. I think you guys use square brackets, so square bracket negative infinity to negative 1, excluding negative 1, union negative 1 to 2, excluding negative 1 and negative 2, union 2 to 3. Let me just erase this. As you can see, it's a lot longer to write it this way. I wouldn't do it this way. And then union from 3 to infinity, excluding. Okay. This and this mean the exact same thing. I would go with this notation, it's easier, all real numbers except those ones, or this is perfectly fine as well. Okay. This is another very typical example or problem asked when dealing with continuity. So they ask us to find the parameters a and b to make the function f of x continuous. So if we look on each segment, we have x plus 20 for x values less than 0, ax plus b if x is between 0 and 2, and 10 minus 2x if 2 is less than x. So the first thing to notice that in this case, all three functions here are linear functions, so they're continuous on their domain, so that's fine. So really the only issue that we have here is to ensure that when we stop using this function here at 0, when we continue this function here, ax plus b, we have to ensure that it ends up being at the same spot. So namely that at 0, at the break of 0, the left-sided limit and the right-sided limit have to meet. This is what we have to ensure. Okay. And similarly at the break of 2, when x is 2, we have to ensure that when we finish using this function here, the ax plus b, and we start using this one, it occurs at the exact same value. Okay. So let's go ahead and do that. So step 1, we want to ensure that the left limit as x approaches 0 from the left side of this function is equal to limit as x approaches 0 from the right side. From the left side of 0, we're using this function here, the x plus 20. So the limit as x approaches 0 of x plus 20 is equal to the limit as x approaches 0 from the right side, this is the left side, of ax plus b. Substituting x with 0, we get 20 on this side, and that's equal to, substituting x with 0, we get a times 0 plus b. This tells us that solving for this, b is equal to 20. So we found our perimeter b. Now we have to go find perimeter a. Typically what you do in these types of problems is that you have 2 equations, 2 unknowns. So in this case it worked out that we actually ended up getting b as the actual numerical value for b. But typically you get 2 unknowns and you get 2 unknowns and then you have to use systems of equation. But it's the same concept. So part 2, we're going to set the limits equal to limit as x approaches 2 from the left of this function here, and we're going to ensure that it's equal to the limit, the right-sided limit at 2 of this function here. Okay, so now I'm not putting a question mark because it's asking us to ensure that this becomes continuous. So this needs to be satisfied in order for the function to be continuous. So ax plus b equals limit as x approaches 2 from the right, f of x is 10 minus 2x. Here we actually solve for b so we could substitute it. So we get a, replace the x with 2, and b we know from over here is 20, so plus 20. And that's equal to, here we're going to substitute it, 10 minus 2 times 2. So a times 2 is 2a plus 20 equals 10 minus 4, 2a equals, this is 6 minus 20. So 2a equals negative 14. Divide both sides by 2, I don't have room, so I'm just going to write it here. A equals negative 7. Okay. So those are the parameters a and b to make the function continuous. So in the middle line here, it's going to be y equals negative 7x plus 20. So a y-intercept of 20, and its slope is going to be negative. It's going to go downwards. And this is our answer. Okay. Let's keep practicing and let's look at our last example. Okay, so in this example here, it's asking us to find and state the types of discontinuities. So we have to find all of the types of discontinuities and actually state which type we're dealing with here. So here's a little trick to keep in mind how to know which one's which. So remember, our 3 types are removable discontinuity, we have jump, and then we have infinite. Really the 2 difficult ones to distinguish are removable and infinite. Jump discontinuity, what you're going to have is essentially a criteria 2 for continuity is going to fail. So we'll essentially have that the limit as x approaches some value from the left is not going to equal the limit as x approaches the same value from the right. Okay, so we know it's a jump when the left-sided limit and the right-sided limit are not equal. It's going to be at different values. Typically we have a jump here, so this is what you're looking for. The ones that are difficult to catch are removable versus infinite. So removable, remember it's a point that's either not defined or it's off the image that you have in mind. You have essentially a hole, or the point could be defined as well. Versus infinite, which recall is something like this with an asymptote. How do we know which one we're dealing with? Well, essentially what we have in both cases are indeterminate forms. This one over here, you'll have an indeterminate form of 0 over 0. Okay. So if you get the indeterminate form 0 over 0, or essentially when you take the limit and you plug it in, wherever this x value is, let's say a, when you plug in a, you'll get 0 on the top, you get 0 on the bottom. This is a hole. This is a removable discontinuity. Whereas for infinite, what you're going to get is the indeterminate form, if. You'll get a number over 0, some number over 0, essentially infinity. If you get infinity, you're dealing with an infinite discontinuity. Okay, so these are the three cases that we have. 0 over 0 is removable. If the left limit and the right limit do not equal, typically it's a jump, and infinite when you have 0 on the denominator, but you end up getting a number on the top. Okay, so keeping this in mind, write this on the side. Let's go ahead and solve this problem here. I'm going to erase this. Yeah, so let's erase, and let's go ahead and solve. So again, over here, keep in mind we have a piecewise function, 2 over x plus 1 if x is less than 1, and then if x is greater or equal to 1, we're using 2x minus 6 over x minus 3. Okay, so again, we have fractions, so what can't we have in a fraction? If we have a fraction, we can't divide by zeros, so case 1, we know that x plus 1 cannot be equal to 0. This denominator at the bottom here cannot be equal to 0. What value would cause it to be equal to 0? Well, bringing the 1 over, x cannot be equal to negative 1. Okay, is this an issue? If you're saying yes, that's too early. Remember, you have to ensure that this x value here falls in the domain. We're using this function here for all x values less than 1. Is negative 1 smaller than 1? Yes, in this case it is. So you have to ensure that this discontinuity is in the domain. Okay, so in this case we do have a discontinuity. Okay, so this is a discontinuity. So we've seen this already, but what we haven't seen is now how to label it. How do we name it? What type of discontinuity do we have? Well, essentially what you're going to do is take the value at negative 1 and plug it back into the function. When you plug it back in, what do you get? Plugging it back in, we get 2 over negative 1 plus 1 is 0. We get a number over 0. So therefore, we have an infinite discontinuity here. Okay. So x equals negative 1 is an infinite discontinuity. Next, we could check the denominator here on the second branch. So 2. So our first thing is an infinite discontinuity at negative 1. Here, the denominator is 3. It's x minus 3, so x minus 3 cannot be 0. So bringing the negative 3 over, you get x cannot be equal to 3, positive 3. That's an issue. Okay, so again, how do we know if it's infinite or if it's removable? We plug it back in. So we have discontinuity at x equals 3. Which type is it? Well, plugging it back into here, you get 2 times 3 minus 6 over 3 minus 3. This gives us 6 minus 6 on top is 0. On the bottom, 3 minus 3 is 0. So we have the discontinuity of the form, or an indeterminate form, 0, 0 over 0. Therefore, we have a removable discontinuity. And the last that we have to check is for jump. So for a jump discontinuity, you have to ensure that the left-sided limit and the right-sided limit, this break at x equals 1, do the two functions meet? Do they touch? So in order to do that, we take the limit as x approaches 1 from the left side of the function and check if it's equal to the limit as x approaches 1 from the right side of the function at 1. So the left-sided limit, we're using the top function because it's smaller than 1, 2 over x plus 1. And here we're using the right side of the limit. By now we should be comfortable with this. We've seen this multiple times. 2x minus 6 over x minus 3. Okay. So substituting x with 1 here, you get 2 over 2. And is that equal to, here what you could do is factor out a 2 on top, and you're going to be left with 2 times x minus 3 over x minus 3. Notice that the x minus 3 cancels and we're left with 2. So is 1 equal to 2? False. Therefore, we have a jump discontinuity at x equals 1. Okay. So these are the three types of discontinuity that we had. We had all three cases in this one example, and we were able to label them. Also, if it asks us to find the interval of continuity, so we found where the function is discontinuous. If you wanted to find the interval of continuity where it's continuous, ILC, this wasn't asked, but I'm just adding it. It's going to be all the values except the ones that we found. So all real numbers except at x equals -1, x equals 1, and 3. Okay. So I hope this helps, and keep practicing.